So what we're going to do in section 6.8 is we're going to prove the inverse function theorem. That was the theorem stated at the end of the last video. There is a proof in your book, but I think it goes a little too fast. I think it's a little confusing, and it doesn't have and I don't like any of the homework exercises. So what we are going to do is we're going to prove the implicit inverse function theorem a little bit more slowly, and you're going to prove a bunch of pieces of it on the homework, both your homework from the last video and your homework for this video. So the thing I owe you, the thing I promised you at the end of the last video, was I define a continuously differentiable, and it's going to take us a little while to get there. So let's start by recalling some definitions that I have stated somewhere in chapter 6, but we didn't do section 6.4 in detail, so I'll describe this again. This is a definition from the very start of section 6.4. If you have a paper book, this is on page 173. If you've got an ebook, you're just going to have to page through at the start of section 6.4 or just watch this video. L with the script L of RP, RQ. That's the set of all linear functions from RP to RQ. So that's all the functions from P to Q that are linear. And this is a vector space. I should mention if we only write one RP, it's understood that RP is both the domain and the range. Then this space is a vector space. We define scalar multiplication. A scalar, if alpha is a scalar, then and A is an element of our vector space, then A alpha V, that's another linear function. That's just alpha times AV. And if we have two A and B linear functions, their sum, we just add pointwise. And that gives us another sum, and I'll leave it as an exercise to check that that alpha A and A plus V are in fact still linear, and that all your usual axioms of vector spaces still hold. It's actually a normed vector space. We've seen the definition before, or you can look it up in your book. If A is a linear function, then the norm of A, that is going to be the supremum. There are several different equivalent definitions. It's the supremum of, you take A of X and you take the norm. That's the supremum of all X in the domain where the norm of X is less than or equal to 1. And you can prove that this is the supremum of A of X divided by the norm of X, where X is in your domain. X is not equal to 0. And then there is a proposition. This is from video lecture 6.5.1.3. It's sort of stated, it's sort of nodded towards in your book, but I think I worked it out in a little bit more detail in the video. If A is any linear function between two finite dimensional vector spaces, then the norm is finite. Is not equal to 0, and lambda is such that, let's use a different letter. Such that AY is less than lambda Y, then in particular, AX is less than or equal to lambda X, or AX over X. It's less than or equal to lambda. So everything in here is less than everything in here. And therefore, the supremum of the first set is less than or equal to the infimum of the set. I think I'd like to say a little bit more about this norm of A. It is also the smallest value, capital lambda, in the real numbers, such that norm of AX less than or equal to capital lambda times X for all X in RP. So this inequality is true with lambda replaced by capital A, and so if it's true for any capital lambda, then lambda is at least big A. So let me go ahead and state a proposition. The three formulas above for the norm of A are equivalent. Let's go ahead and prove this. We have that if X is in RP and the norm of X less than or equal to 1, then either X equals 0 and any linear operator of 0 is 0 and the norm of 0 is always 0, or we've got that AX is less than or equal to AX over the norm of X. So we have that. Our first supremum is less than or equal to our second supremum. And then if x, finally, we'll call it lambda twiddle be that first supremum. And then if y is in Rp, then we can write either y is equal to 0, so norm of ay, y is 0, so ay is 0, so the norm of ay is 0. That's less than or equal to your favorite number times 0. It's a supremum of non-negative numbers, so it's certainly non-negative. Or y is not 0, so the norm of ay, that's the norm of a of y over the norm of y times the norm of y. And then because a is linear, we can move the norm of y out of a. Then because this is a norm in Rp, we can move our constant out, our scalar out front. And then y over the norm of y, that has norm 1, so this is at most norm of y times our lambda twiddle. So lambda twiddle is in our set of all real numbers lambda such that ay less than or equal to lambda norm of y for all y. So in particular, that means that the infimum of our lambdas that's less than or equal to our lambda twiddle because it's one of the lambdas, which is the supremum of our ax's. Which now we recall that was less than or equal to the supremum of the quotients. Which is less than or equal to our infimum of the lambdas. So all three of them must be equal, since we've got this chain of inequalities which has the same thing on two of its ends. And what's more, since our lambda twiddle, since lambda twiddle is in this set that we're taking the infimum of, it must be not only an infimum, it must be a minimum. So that completes the proof. Here is another proposition. The proof of this is an exam study problem. This is a norm on the vector space of linear functions, that means that if alpha is a real number and A is in our vector space, then the norm of alpha A is alpha, or its absolute value rather, times the norm of A. And if we say that the distance from A to B is the norm of A minus B, that is, if that's how we define that, then D is a metric, so positive, definite, symmetric triangle inequality. The proof of that is left as an exercise, and ideally you would have seen something like this in your linear algebra class. Okay, but the point is now we've established that this space of all linear operators, now it's a metric space, so we can talk about continuity. So let's let X subset of Rp be open. F goes from X to Rq. And let's suppose that F is differentiable at C for all C and F in X. That is, df of C exists for all C and X. And the reason I wanted this open is that then I can say by proposition 6.4.2, df of C is unique. We remember from homework 20 that at weird boundary points you might have many different derivatives. If X is open, df of C is unique. So we can think of df as a function whose domain is X and whose range is L, is our L of Rp. Rq, remember, df of C is always a linear operator, so df is a function from our C's, which is X, to the set of linear operators. And it is well defined, meaning that if there is only one possible output for any input, that's why I brought up proposition 6.4.2. And then if df is continuous as a function from X to our linear operators, we say that f is continuously differentiable if you need to specify it's continuously differentiable on X. This is definition 6.5.11, sorry. Now I am going to prove a lemma which is going to do a lot of the work. It's going to be one of the major steps in proving the inverse function function theorem. It's going to be somewhat involved, but it is a thing we are going to need. So let's let omega be an open subset of RP. And we'll let f be a function whose domain is omega and whose range is RP that is continuously differentiable. And such that df of x, that linear operator is invertible. It's an invertible linear transformation for all x in omega. And the conclusion is that then f of omega is an open set. And you may remember the proof of the inverse function theorem has an f of u is open as one of its conclusions. We'll use this there. We'll use it in other ways. And this bit where df of x is invertible for all x in omega, you will prove something like that on your homework for tonight. And we'll see in tomorrow's video how we put together all these things to get the full inverse function theorem. Well, let us pick some point y naught in f of omega. And then by definition of f of omega, y naught is equal to f of x for some x in our domain omega. And now because f is continuously differentiable and df of x in particular is invertible, we're going to let epsilon, we'll define that as 1 over 2 times the operator norm df of x inverse. This is, in fact, a linear operator, df of x, and it's not too hard to show that no invertible linear transformation can have norm 0. The only linear function that has norm 0 is the 0 function, which isn't invertible, so epsilon is a positive real number. And let's let delta be such that two things are true. First, we're going to say that the ball centered at x of radius delta, let's make it the closed ball, is it in omega? That'll make a few things more convenient. You can do this by proposition 5.3.3 and such that it's the delta in the definition of continuously differentiable, such that df of x minus df of w is less than this epsilon for all w in this ball. And now let's let r be epsilon times delta. What we're going to do next is that we are going to show that the ball centered at y naught of radius r is contained in f of omega. And because y naught is an arbitrary point in f of omega and r is positive, by proposition 2.5.3.3, this is enough to show that f of omega is open. It is that every y naught in f of omega, you can draw a little ball around it of positive radius that's in f of omega. So that's how we're going to prove openness. And here is how we are going to do this. We are going to choose, or rather direct our reader to choose a point y in our ball y naught of radius r. And what we want to find is an x, or rather a w, such that y is equal to f of w, where w is an omega. And let me draw a picture of what's going to be going on here. So here is our x-axis. Let's say our x-axis is omega, and then here is our f of omega. And here, so this is a one-dimensional picture of what's going on. We'll put our point x here. So up here we've got the point x comma f of x. And then df of x, we remember, is a linear function. So you can visualize that as being the tangent line, which now has slope df of x. Let's extend this a little bit further. Let's put our point y that we're trying to get at here. Then we can draw a nice long straight line through our graph, and that's where we're trying to get. And then here's what we do. Because this is a linear function, we can invert it easily. So what we do is we don't try to find this point right away. We try to zoom in on it slowly. So we find this point here. We'll call this point here, we'll call this W1. And that's our first approximation. And then we see that isn't quite right. F of W1 isn't y, it's down here. So we approximate again. We draw our affine function through that point. And then we can solve our affine equation. We find our W2. Then we go up to, that isn't quite right again, so we do it the whole thing over. We just keep we keep making W approximations and getting better and better. Zooming in, and at least is the theory. Getting closer and closer. So that's the idea of what I'm about to describe algebraically. So we're going to let W naught equal x. And then we're going to say that if W sub n is a point in omega, we're going to let W sub n plus 1 satisfy. Now Right, y equals f of wn. Then we add to that our invertible linear function evaluated at wn plus 1 minus wn. So that's getting back to this picture. If you look at this picture, you can see how this is related to it. Or if we go ahead and solve this for wn plus 1, that's wn plus invertible linear transformation. It's inverse of y minus f of wn. So now I am going to claim two things which will let us complete the proof. So notice in our picture, the WNs are sort of getting closer and closer to each other. The F's of WNs are getting closer and closer to Y, and the WNs, they never get too much further than X than they started out from. So we're going to prove by induction that that is actually true. So we're going to need a Wn minus X is less than delta. This extra 1 minus 1 over 2 to the n, we're going to need that in the induction step to prove it for Wn plus 1. So Wn is in omega, since it's in the ball centered at x of radius delta. And a minus f of x Wn, that thing is going to be less than r over 2 to the n for all, and this is for all natural numbers n, natural numbers or 0. Now let's prove the claim. First off, it is obviously true for n equals 0. W naught is indeed 0, is indeed x, so this is 0, and y is chosen to be in the ball centered at f of x of radius r. So y minus f of w0, that's y minus f of x, less than r, that's r over 2 to the 0. So we've got our base case. Now, basic induction, we suppose the claim is true for n. All right, the first thing to notice is that y minus f of wn, that's less than r over 2 to the n. So, well, let's write this out. Wn plus 1 minus wn. That we remember solving for that df of x inverse of y minus f of wn. And by our definition of operator norms, this is at most df of x, operator norm inverse, times the norm of the input, y minus f of wn, which we remember that the operator norm is defined to be 1 over 2 epsilon. which by our induction hypothesis is 1 over 2 epsilon times r over 2 to the n. And then r is epsilon times delta, so this is delta over 2 to the n plus 1. So then we get our condition on Wn plus 1 by the triangle inequality. And then we get exactly what we're supposed to get. Actually, that's so important, we'll go ahead and add it to our claim. Now we need the other piece. This is going to be the most involved part of the proof. Y minus f of Wn plus 1. We're going to subtract and add f of Wn. And then we remember what y minus f of Wn was. By definition, that's df of x evaluated at Wn plus 1 minus Wn. Then we've got our other piece here. So we've got a function, it's this df of x minus f function, and we want to look at its differences at two values, at Wn and Wn plus 1. And the good tool we have for looking at differences of differentiable functions is the mean value theorem. But the mean value theorem is a fundamentally one-dimensional thing. It just doesn't work at all in higher dimensions. So we're going to have to massage this so we're only looking at one dimension. Let's define gamma of t. This is what we did in the proof of lemma 6.6.6. Gamma of t, we'll let that be Wn plus t times Wn plus 1 minus Wn. And then gamma is a function that goes from, well, all the real numbers, but what we care about is the interval 0, 1 into omega. See, if we look at this, here's our point x. Here is our ball centered at x of radius delta, which we remember is contained in omega. And we've just worked out that Wn and Wn plus 1 are both in this ball. Then gamma of 0 is Wn, and gamma of 1 is Wn plus 1, and gamma of 0, 1 is this straight line. So this straight line is certainly in the ball, so it's contained in omega. So in particular, f of gamma of t exists for all t between 0 and 1. Now we need our output. We're going to let a be any constant vector. A is an element of Rp, and we'll let g of t be f of gamma of t. We'll take that and we'll take the inner product of A with A. So that's the inner product of f composed with gamma of t with A. And the reason why we're taking the inner product is that now g is a function whose domain is an interval in the real numbers and whose range is now the real numbers. F maps into Rp, but taking the inner product with A, we map into the real numbers, which is good. That's where we want to be mapping. And then, so now we can apply the mean value theorem to G. So to apply the mean value theorem, we need to know the derivative of G. So S times G prime of T, where that's the derivative in the sense of one-dimensional functions in the sense of chapter 2. This is dg of t, the linear function, the derivative in the sense of chapter 6. And then you plug in as input the number s. And this is by proposition 2.2.9. And then remember lecture 6.5.1.2 when we were talking about breaking derivatives of functions into derivatives of their components. If you trace through that, you'll see that the derivative of an inner product with a constant, it's very much like multiplication. It's the inner product of A with the derivative of this function, f composed with g of t, and then you evaluate it at the point S. We can evaluate this derivative by the chain rule. Sorry, that needs to be a gamma. df of the point gamma of t composed with d gamma of t whole thing of s that's by the chain rule. And then you know what d gamma is. This is the inner product of A with df of gamma of t. That's a linear operator. And then d gamma of t, we know what that is. That's just wn plus 1 minus wn times the scalar s, which we can go ahead and pull out. And then pulling this s out, canceling the s, we discover that our g prime of t is equal to df of gamma of t, that linear operator, evaluated at the vector wn plus 1 minus wn. And g is continuous on the unit interval. So by the mean value theorem, there is a t in 0, 1 such that g of 1 minus g of 0, I'd have to divide by 1 minus 0, except that's 1, is g prime of t is df of gamma of t, evaluated at wn plus 1 minus wn. Sorry, I have forgotten a bunch of inner products with A. And then on the other side, we've got inner product with A of f of wn plus 1 minus f of wn. Let's summarize. Let's put this all together. So if we have a constant a vector in Rp, then there is well, there is a t between 0 and 1, but then gamma of t, remember, is a point in our ball. So let's let z be our gamma of t. Z is in the ball centered at x of radius delta, such that if we take the inner product of A with the thing we care about, that is, we remember the inner product of A with, we worked out, this comes out to df of x of wn plus 1 minus wn. Then because the inner product with A is linear, we can just add on our second piece, a f of wn. Let's make it wn plus 1 minus f of wn. And we can do that because I have made this, if we make it a minus sign, and then let's plug in what we just did all that work for. Inner product of A with df, now not of x, of gamma of t, which means of z, but then the same input. And then because everything is linear, inner product with A is linear, we can turn this into the inner product of A with this difference, df of x minus df of z. That's a or rather difference of linear operators. So it is a linear operator, wn plus 1 minus wn. And then, so let's take some absolute values. A minus inner product of A with y minus the f of wn plus 1, inner product of A with the thing we care about. Then by the Cauchy-Schwarz inequality, that's at most A times then the other thing. This is at most the linear algebra operator norm, df of x minus df of z, times wn plus 1 minus wn. And we remember that because f is continuously differentiable, df of x minus df of z is less than epsilon. And our wn plus 1 minus wn, and we've worked out, is less than r over 2 to the n plus 1. Then epsilon times r is a. Sorry, this is a delta over 2 to the n plus 1, and epsilon times delta is r. So we get an r over 2 to the n plus 1. And then just let A be the vector we care about again. And then the inner product of a vector with itself is its norm squared. Or canceling this out, we get the y minus f of wn plus 1. Either the norm is 0, so it's certainly less than r over 2 to the n plus 1 because r is positive, or it's not 0 and I am indeed allowed to cancel, and this completes the proof of the claim. Actually, that's so important. Let's add it to our claim. let's remember what we were trying to prove here. We've picked a point y in our thing that we're trying to claim is contained in the image, and we're trying to show that it's an f of w for some w. So we've established that Wn, it's a subset of the ball centered at x of radius delta, and it is Cauchy. So Wn converges to W for some W in our closed ball. This is why I wanted a closed ball, which is contained in our open set omega. F is differentiable everywhere, so it is continuous at W. And that we remember we proved it back in section 6.5. So f of Wn converges to f of W. But f of Wn also converges to y. So y equals f of W. Thus, y is in f of our closed ball. That is, it's in f of omega. And since y was arbitrary, we've got that the ball centered at f of x of radius r is contained in f of omega. And thus, f of omega is indeed open.